We're going to start with today taking a look at whether it's possible for an object to be in a state of equilibrium with three forces with three different magnitudes acting upon it. So the first thing I want to address is what the state of equilibrium means. So it means when I apply, three forces onto an object, okay, that when I add them all up together, we would end up with the zero vector. So we wouldn't actually move anywhere. Okay, so we would end up into the same spot that we started with. So that's our kind of idea. So if I have, this is vector A, B, and C, and I'll just go ahead and think about A, B, and C, where I have the magnitudes 10, 20, and 90, will that give me a state of equilibrium? So basically, if I were to, can I arrange them in a way so that they all add up to the zero vector? Basically, we go back to our idea of, can we build a triangle? So if I'm given three sides or three side lengths, and in this case, that would be our magnitudes, can we build a triangle? And that's, if we can build a triangle, then we know that we can be in a state of equilibrium. So how do we know if we can build a triangle with three sides? So basically, our triangle inequality theorem says that if I have the sum of two sides are greater than the third side for all cases of all three sides. So if I have A plus B greater than C, B plus C greater than A, and A plus C greater than B, then I can build a triangle. Okay, so I know that if my magnitudes, if I just take a look at my magnitudes and the sum of two sides is greater than the third side for all three combinations, then I can build a triangle. Therefore, I can be in equilibrium. And this is only true if all three of these exist. Okay, so all three must exist or must hold true to build a triangle. So I want you to take a quick look at these three cases and see which of the following sets of forces acting upon an object could produce an equilibrium. So feel free to pause the video and just do some quick math and see what you think. Okay, so after you've taken a look at it on your own, hopefully you were able to figure out that this first one, yes, we can build a triangle, and so therefore we can produce equilibrium. The second one is also a yes. This third one, question C, is a no. Now this last one is interesting. This one doesn't create a triangle, so not a triangle. But in fact, so let's just take a look at the sum of the sides and compare them to the third side. So obviously 10 plus 19 is greater than 9. Okay, so that's fine. 9 plus 19 is greater than 10. That's fine. But when we do 9 plus 10, that actually equals 19. So it's not greater than 19. But because it's equal, we can still, I want you to think about getting back to that same spot or that zero vector. Although we don't build a triangle, so don't build a triangle, we still do have equilibrium because we will end up back at the same spot. Okay, so in this one, now we're going to take a look at how we resolve forces. And we're going to take a look at this example. So a girl pulls on a rope attached to her sled with 50 Newton force at a 30-degree angle to the horizontal. So I'm going to start by drawing a sketch of this situation. So here I've drawn my horizontal line in black, and then I've shown the force of 50 newtons acting at 30 degrees angle, acting at a 30-degree angle to the horizontal. Okay, so there's my force there. Now, we can actually resolve this force into components. So I'm going to break down that 50 Newton force into two parts. So I'm going to start by redrawing that horizontal line. And I'm going to draw that force. I'm going to try and keep it as similar as I can. And I'm going to break it down into two other forces, a vertical and a horizontal force. So I'm going to start by drawing my horizontal force along the bottom. Hopefully you can kind of see that there. And then my vertical force up to the top. And so we are going to go ahead and label these. So this will be our original force as vector F, and then we'll call this the horizontal force or the horizontal component, and force vertical or a vertical component, okay? So what we're doing here is we're resolving that force F into two different components. So let's take a little note on this. So we say that F, so the force F can be resolved that's an R there, into components. So in this case, we have the horizontal, which is F horizontal, and vertical, F vertical. And these ones are actually called regular, or sometimes they're called rectangular components. So you'll see them referred to both. So rectangular components. And that's because they're perpendicular to each other. So they're at 90 degrees to each other. So because they are perpendicular to each other. Okay, or they're at 90 degrees. Okay, perpendicular. Okay, so let's take a look at an example. So we have a force of 40 newtons acting on a bearing of 30 degrees. Resolve the force into its horizontal and vertical components. So this is very similar to what we would set up. So let's start by drawing a picture of this force. So I'm going to start by putting our axes down, so north, south, east, west, and drawing a bearing, a true bearing of 30 degrees. Okay, so I've drawn my axes and I've added my force. Now, just to include some more information on my diagram, so I know that this is 30 degrees for my bearing. I also know that the magnitude of that vector is 40 newtons. And so now I'm going to break it down and resolve it into its horizontal and vertical components. So remembering that what this means is that I want to find the magnitude of my force horizontal and my force vertical, okay? Okay, so let's first go ahead and draw those. So this is my force horizontal. And I'm a little bit off here on my diagram. there's my force vertical. Okay, I'm also going to add in 60 degrees in here and recognize that this is a right angle triangle. So this is a 60-degree triangle.
90.
So to find my magnitude or my vertical components, and again, we know the direction that they are, right? They're horizontal and vertical. So to find those magnitudes, I'm going to go ahead and use trigonometry, right? So in this case, I'm going to use trig ratios. So to find my force vertical, I'm going to use sine of 60 degrees is equal to my magnitude of that force, that vertical force, all over 40 newtons. And then I'm going to get approximately 34.64 newtons. Sometimes you'll just see the answer written as, so for an exact answer, if we wanted an exact answer, we just write it as 40 sine 60, okay, or 40 times sine 60. So this would be our exact answer. This would be our approximate answer. So to find my force horizontal, I would do cos of 60 degrees is equal to that magnitude all over 40. And again, that would equal 20 newtons. You could also write it as 40 cos 60 as an exact answer. Okay. Now we're going to take a look at a specific example where we're looking at mass on a ramp and the forces that are working against this object, okay? So first we're going to draw a picture of what's going on. So we have an object that has 50 grams, a mass of 50 grams on a ramp inclined at an angle of 30 degrees to the horizontal. So let's draw that picture. So in my picture, I have the horizontal line, the ramp is in red, you can see that it's 30 degrees to the horizontal, and my object I'm just representing with that blue dot. So now I'm going to go through the three forces that are acting on this object. So the first one that we're going to talk about is the force of gravity. So this force of gravity, obviously it's going downwards, so we can draw it on here like this, and I'm going to label it F subscript G, so force of gravity. And over here, I'm going to make a little note on that force of gravity. And I want us to make a little note here that this is always mass multiplied by 9.8, so that gravitational constant. And this mass needs to be in kilograms. And that will give us our force in newtons. Okay, so that's our first force. The next force that we're going to draw is what we call our normal force. And so this normal force is acting on a perpendicular to the ramp. Okay, and I'm going to label this F subscript N. And again, this is our normal force. And this is sometimes referred to as the contact force. And just as a reminder, this is 90 degrees to the ramp. Okay, and then our last force that we're going to add here is the force of friction. And I'm going to label that F subscript F. So our force of friction, and that's always parallel to the ramp. So sometimes we call these forces, so this one here, we would call this force perpendicular and force parallel. Those are also words that come up. So, but we need to think about them as the perpendicular force to the ramp and the parallel force to the ramp. So let's move on to part B. We're going to resolve the force of gravity into regular components that are parallel and perpendicular to the ramp. So we're going to start with that force of gravity, which we know is going downwards. And I'm just going to draw a bigger picture here. So this is my force, that's a G, my force of gravity. And then we would resolve it into the perpendicular force and the parallel force, okay? So there's a couple different ways to kind of think about this. We can draw, hang on. So we can draw our perpendicular force. So sometimes you'll see this written like this, so F perpendicular or F perpendicular, you'll see it written like this. But we also know that this is in the other direction of the ramp. So remember our normal force was going in that direction. So this one here would be negative F of n, F subscript n, so our normal force. So it would be the opposite of the normal force. And then we can draw the other force, F parallel. So you'll sometimes see it written like this as F parallel, but we also know that this is opposite to that force of friction, right? So this is negative F subscript F. So either way would be fine to think about it. But basically, in order for something to be in equilibrium though, all of these three forces we would put back to zero, right? So like our gravitational force plus our normal force plus our force of friction would go ahead and equal to zero. And when I'm talking about that equilibrium, oops, I'm talking about those three up there. Okay. So now let's take a look at if the object is at rest, then what must the magnitudes of the force of friction and the normal force be equal to? So let's go ahead and draw our diagram again, where we have that horizontal, the 30 degrees, and our object on that ramp. So here's my diagram again. I know that this object has a mass of 50 grams. So the first thing I'm going to go ahead and do is find that gravitational force. So I know that my force of gravity is going to be 0.05, because remember this 50 grams, it needs to be in kilograms, times 9.8. So I get 0.49 newtons. And of course, that force of gravity, that's down. And so we can add that to our diagram. Now, in order for our object to be at rest, which basically means that we need three forces to be in equilibrium, and that would be this gravitational force plus our normal force plus our force of friction. But we can resolve this gravitational force into our two forces, our perpendicular force and our parallel force, so that the sum of those two will equal this gravitational force. So this might be a little bit confusing. Let me explain that a little bit better. So we have our normal force that's up here. we have our force of friction that's up here. So when I take a look at adding those three together, right, they should equal 0. So an easier way to think about this is going ahead and thinking about what two forces added together would give us that, would be equal to that force of gravity. So we tend to think about looking at what we say as the force perpendicular, which is this one, which is the opposite vector to the normal force, and force parallel, which is in the opposite direction again to that force of friction, okay? And this is 90 degrees here, so we're resolving that gravitational force into two components, force perpendicular and force parallel. So what we need to do is go ahead and find the magnitudes of those two forces there. Okay, so I'm going to do a little bit of work over on our diagram. So if I know that this is 90 degrees, this here is 30 degrees, I know that this here is 60 degrees, this inside the triangle here, I know it's a bit small, must be 30 degrees. So in that triangle, we now have a 30, 60, 90 triangle as well. Okay, just keeping in mind that that's 90 degrees there too. So I'm solving that triangle that I just drew, that 0.49 newtons and force perpendicular and force parallel. And so to solve that triangle there, and hopefully you can kind of see what I'm talking about. So this triangle here, we're going to use our trig ratios. Okay, so I'm going to set up first. So the cosine of 30 is equal to the magnitude of that force perpendicular all over 0.49. And when I go ahead to solve for that, I end up with the force perpendicular as being equal to 0.42 newtons. So same idea when I'm finding the magnitude of force parallel. So the sine of 30 degrees is equal to the magnitude of that parallel force over 0.49. So I end up with the magnitude of force parallel being 0.42